Good morning, guys. Today we're going to look at factoring quadratic expressions. So let's just start talking about what actually factoring is. As we can see here, factoring is rewriting an expression as the product of its factors. Well, what is a factor? Factors are just expressions which are multiplied together. So it's taking this large expression, we're going to work with quadratics today, so a sum of terms up to something squared, and we're just breaking it down into the smallest pieces that we could re-multiply together and put us back where we started. So it sounds kind of circular in definition, but it is really that simple as far as something big, breaking it into the product of smaller pieces. So let's just start with a number and just talk about this idea of factoring in. Let's say we had the number 300. We wanted to completely factor 300. So to figure out how to, or what 300 completely factored is, what we want to do is just divide it out, or figure out what pieces we could put together, what numbers we could multiply together to create 300. Well, you've been doing this for many, many years with factor trees. So we're going to use that same idea here. So 300, you could pick any number of products. That would give us 300. 30 and 10 is probably the most obvious. Sorry. 30 and 10 is probably the most obvious. So we then break down the 30. 30 is 6 times 5. 6 will continue to break down. 2 times 3. So we have 3 factors of 30, none of which can break down into anything other than 1 in themselves. These are prime numbers, so they're completely factored. 10 we can factor down into 5 times 2. And 5 and 2 are now prime. They can't break down anymore. So what we get is this collection of factors down here at the bottom. So we could say 300 is equivalent to 2 2's. So that's 2 squared, 3, and 2 5's. That's 5 squared. So this is the completely factored form. You would have called that the prime factorization before. This is the completely factored form of the number 300. We're going to use this same idea of completely breaking expressions down, factoring them out, until we get small expressions that will not factor out anymore. We're going to translate that into quadratic expressions here in a minute. Okay, guys, first type of factor we're going to look at is just common factor. Common factor means we have a factor of every single term in the expression. So everything, remember, a term is things that we're adding together, a factor is things we're multiplying together. So if every term has the same factor, it means every term was multiplied by the same expression. So if we look at these few examples, where I've got 3a squared plus 9, we can see that both the first term, 3a squared, and the second term have a factor of 3, meaning 3 can divide into this, leave no remainder. 3 can divide into this, leaving no remainder. So typically when we write this, we'll put this divided by 3. Now, it's not going to just disappear. What we're doing is we're identifying what that common factor is, and we're dividing it out of the expression to see what expression remains. So if I divide the 3 out of each expression, my 3 has now been factored out, and when I remove the factor of 3 from the first term, I'm left with a squared, because 3 divided by 3 is 1. So I'm left with 1a squared. And when I factor the 3 out of the second term, 9 divided by 3 is positive 3. So my expression that's remaining is a squared plus 3. A squared plus 3 is not the factored form. 3 times a squared plus 3 is my factored form. And we can see that by if I recombine, if we redistributed this 3 times a squared is 3a squared, 3 times 3 is 9. It would put us back where we started. So that's all factoring is. It's just identifying what smaller expressions could we redistribute, could we remultiply to create this larger expression. So common factor, both of them could divide by 3 and have no remainder. So we just divided a 3 out of each term. Let's look at number 2. Same idea. What's the common factor in each of these? Well, 5 and 7 don't have a common factor, but x squared and x do. Both of those can divide by an x. So if we factor out an x, divide x out of each term, so we were left with 5x, because I have x squared, and I divide 1x away, I'm left with x to the first. 7x, and I divide the x away, I'm left with a 7, and that's removing the common factor of x. Again, we could redistribute to check. X and 5x is 5x squared. X and 7 is 7x, and that puts us back where we started. So this is the correct factorization. Let's go to number 3. We have 3 terms. Negative 5x squared plus 10x minus 45. When we look at it, they don't all have an x, so there's not a common factor of x, but they do all have coefficients that will divide by 5 or negative 5. So we could go either way. And it really depends on what else you're going to do with the problem after this. If the problem just said factor, you could do either one, negative 5 or positive 5 for the common factor. I'm going to do negative 5 just because I know usually I like that lead coefficient to be a 1, so, or a positive number. So if this is negative, then I'm going to look for a negative to pull out of it. When I factor that negative 5 out, negative 5 divided by negative 5 is 1, so all I'm left with is x squared. 10 divided by negative 5 is negative 2, so negative 2x. Negative 5 divided by negative 5 is positive 9. So that is the common factor of negative 5 removed. Again, I could have gone through and removed a positive 5, which would have given me negative 1, positive 2, and negative 9. Okay? So either one of those factorizations will be correct in that scenario. Again, it just looks up. It just depends on what you're going to do with it afterwards. Usually we're going to start solving and things like that, or doing some further factoring. And it's usually easier if that lead coefficient is 1. But again, personal preference on whether you want to do positive 5 or negative. Now number 4 may look like it's nothing super obvious as what's the common factor is. But if we look at what the 2 terms are, this is my first term. This is my second term. Okay? X and 2 are terms, but they're terms within this first term. So if we're looking at the whole picture, what are my individual terms? X plus 2, quantity squared, minus 3 times x plus 2. Now it should be a little more obvious what's in common to both terms. Well, both of them have at least an x plus 2 in it. So this is x plus 2 to the first. This is x plus 2 to the second. So this one has 2 of them. Well, just like we did up here, we took the common factor and removed it. And what remained, if I had x plus 2 squared, that means there were 2 x plus 2s. Well, I've removed one of them, so I'm left with just a single x plus 2. So there's an x plus 2. Then on the second one, I had negative 3 in x plus 2. We'll remove the x plus 2, so we're just left with the minus 3. And then we can clean it up. X plus 2 plus negative 3 is x minus 1. So this would be the final factored form. And we could check that by distributing, combining like terms here, distributing, combining like terms here, and it would put us at the exact same expression. So this is a few examples of how common factor works, looking at every single term, seeing if there's something that is a factor of each term that we can then divide out, move outside to give us a smaller, easier to work with expression remaining. That's common factor. Okay guys, now we're going to look at quadratic trinomials. Quadratic trinomial is anything on the form ax squared plus bx plus c, where a, b, and c are real numbers. When we factor a quadratic trinomial, we actually factor it into a pair of linear binomials. And that comes just from the idea of what factoring is. It's breaking it up into its multiplication pieces. So if I was to go work backwards and multiply a pair of linear binomials, we would do that by distributive property. Like we do all multiplication is by distributive property. So when I distribute, I'm going to distribute the x to each term of the second factor. So x times 3x is 3x squared. X times negative 5 is negative 5x. Then I'm going to come back and distribute the 2 from the first factor to each term of the second factor. 2 times 3x is positive 6x. 2 times negative 5 is negative 10. Then we're going to combine the like terms together. So I get 3x squared. Negative 5x plus 6x is 1x. And then negative 10. And we get this expression, 3x squared plus x minus 10. So what we can see is that when I multiply a pair of linear binomials, I get a quadratic trinomial, quadratic of 3 terms. So conversely, going in the other direction, if I'm going to factor, which means break up into the multiplication, if I'm going to factor a quadratic trinomial, it should always come out as a pair of linear binomials. If it can factor, and we'll talk later about some quadratic trinomials that won't even factor. Now, let's look at how this actually would work backwards, how we could break this up. Now, if we notice, this first term, 3x squared, came from the product of the first terms. So, ax squared is actually going to factor into dx and fx. Okay? So the first term is going to break up into the first terms. So 3x squared came from our first terms. We can see that our last term, the negative 10, was a product of the last terms. So what we're going to get is the constant is going to factor into the constants. Now there are a lot of different ways I could write negative 10. Negative 10 could have been negative 10 and 1, negative 1 and 10, negative 2 and 5, positive 2 and negative 5. So what is it that tells me that it was 2 and negative 5 that gave me this specific negative 10? Well, it's the middle terms. The middle terms, 2 and 3x, gave me positive 6x, and the outside terms, x and negative 5, gave me negative 5x. So in essence, what we're doing is we're going to factor the first term, 3x squared, into 3x and x. The last term, negative 10, into negative 5 and 2. But it all has to check so that when we combine our inner terms and outer terms, we're going to get the correct middle term. So this negative 1 right here, the middle term, the b of x, ends up being the check to make sure that we've got these factors as the correct numbers in the correct order. So let's kind of go through and see that with an example. Let's look at number 1. 2x squared minus 19x plus 24. Well, it's a quadratic trinomial. So I know I should try to factor it into a pair of linear binomials. And again, we're going to talk later about, for what we're doing right now, they're all going to factor. But we'll talk later when we're doing quadratic formula about when we can factor and when we can't factor. So for what we're doing now, assume they'll all factor. So 2x squared, first term should factor into my first term. So 2x squared would be 2x times x. There's not a lot of options there, okay? Because 2 is 2 times 1, and x squared is x times x. Because remember we said it had to be a pair of linear binomials, so it's always got to be x to the first. Now let's look at the 24. 24 has many, many options. So we could go with 12 and 2. So I can try plus 12 plus 2. Well, if I check that, remember, factor the first number into the first numbers. Factor your constant into your constants, and then you're going to check the inners and the outers to see if it gives you that middle number. So 12x, or 12 times x is 12x. 2x times 2 is 4x. And see how they had to combine to give us that middle number? Well, when I combine those, I get 16x. Does that match the middle number? No. So that means that something's wrong. If your number is wrong when you check, then your numbers have to be wrong somewhere in there. Well, we know 2x and x has to be correct. So it's got to be the 12 and the 2. So I need 2 other factors of 24. Well, let's try 3. Let's try 3 and 8. 3 and 8. Well, let's go back 1 second. Okay. We tried 12 and 2. Let's try 2 and 12 real quick. Because sometimes just flipping the order makes a difference. Because now the 2 is paired with the x. And the 12 is paired with the 2x. So that's going to give us 26x. Okay, still not going to put us at 19. So when I say change your numbers, it can mean get new numbers, or it can mean just flip the order of your numbers. So let's go now and try 8 and 3, or 3 and 8 rather. So 24 is 3 times 8. When we check this one, 3x plus 16x gives us 19x. So the number matches 19 and 19. What's different now is the sign. And well, just a second ago, if we had the wrong number, I needed to change my numbers. Well, if I have the wrong sign, I need to go through and change my signs. So that means just we go opposite. Positive 3 becomes negative 3. Positive 8 becomes negative 8. Well, why can I do that? Well, what's negative 3 times negative 8? It's still positive 24. 24 can factor into a pair of a product of positive numbers or a product of negative numbers. So I just try it out and see which one works. Now, as you do more and more of these, you'll start to see that if this number is positive, it's going to match this sign right here. So product gives me a positive, the sum gives me a negative, so I've got to have two negatives. But if you don't recognize that, just go through, check your numbers, and use that idea of if I need to change my sign, change my sign. So that's going to give me negative 3x, negative 16, negative 19x. So we can now see that this is the factored form of 2x squared minus 19x plus 24. 2x plus 3 times x minus 8. Well, let's go through and look at number 2 the same way. 6x squared minus 5x minus 6. Now, as I look through, that's quadratic trinomial. So we're going to try to break it into a pair of linear binomials. 6x squared, well, there's many things that could give us 6x squared as a product. 2x and 3x, 1x and 6x. So let's try 2x and 3x. 2x and 3x. Now, negative 6. Again, same idea. A lot of products that can give us negative 6. So we're just going to try something. Let's try negative 2 and positive 3. Negative 2 times positive 3. Now, when I try this, we're going to check the inners. That's negative 6x. 2x and 3x is going to be positive 6x. That gives me 0x. Well, middle term needs to be negative 5. Well, what do we say? If I need to change my sign, change my sign. Now, this right here, I could have known before I even tried to check it that it was going to be incorrect because of the fact that 2x minus 2 has a common factor of 2. 3x plus 3 has a common factor of 3. Well, remember, factorization is taking this large expression and breaking it into all the small pieces that factor together, that multiply together to create it. Well, if this smaller piece has a common factor of 2, that means the original expression has to have a smaller factor of 2. The small factors can't have any properties that were not present in the original. They can't have any factors that were not present in the original. Okay, just like the number 30 is 6 and 5, which is 2 and 3. Okay, so 2 times 3 times 5 is the number 30. Well, every single one of those numbers has to divide into the number 30. Well, 2 does not divide into every single term of this expression. So we can't have a common factor of 2 in one of our factors if it's not a common factor in the original expression. So that right there should have been an indicator that I can't use 2 and 3 in that order. I can't pair 2 with 2 and 3 with 3. Well, let's just change the order up. Okay. Let's go with 3 and 2. So when I check this one, I'm going to get negative 9x. Okay. I'm going to get positive 4x. So that negative 9x plus 4x gives me negative 5x, which is what we're looking for in that middle term. So again, we go First term factors into the first terms, last term factors into the last terms, and the inners and outers have to check to give us that middle term. So we get this final, since it all checks out, we get that final factorization, 2x minus 3 times 3x plus 2. That's how we factor quadratic trinomials. Okay guys, we've got two special types of quadratics that we're going to look at now. We can always work the same idea of if it's a quadratic trinomial, break it into a pair of linear binomials, using that idea of factor the first term, factor the constant term, and then check with the inside terms to make sure everything matches up. But if we recognize these special cases, they have just a quick expression or a quick factorization that we can use if we recognize them in their original form. Now, a perfect square trinomial is going to look like this. First term is going to be some number squared. Last term is going to be another perfect square. And the middle term is going to be double the product. So 2 times the product of those first and second terms before they were squared, or the factorizations of those first and second terms. Again, sometimes it's difficult to see, sometimes it's really obvious to see. Now, when we factor that, what happens is I get really just the pair of linear binomials all are exactly the same. So that's why we get this u plus v quantity squared, because the first factor and second factor are going to be identical. Well, let's look at it right here. X squared plus 10x plus 25. This is a perfect square trinomial. If I didn't recognize it as a perfect square trinomial, I could go through and say, break up my first 2 terms. X squared is x and x. 25 is plus 5 and plus 5. So we check it, 5x and 5x gives us the 10x we need. We see we have x plus 5 and x plus 5. So it's x plus 5 quantity squared. That is our factorization. So by the fact that it factors into this, I can see that it's a perfect square trinomial. Let's take a step back. X squared is x and x, so that's a square term. 25 is a perfect square. Okay? 5 and x, if we put those together and doubled that product, we would get the 10x. So if I recognized here that x squared plus 10x plus 25 was actually of this form, where it is x squared, 5 squared, and 2 times x5, okay? It's of this perfect square trinomial form, I could have immediately jumped to x plus 5 quantity squared. And it's a shortcut that's there if you recognize it. If you don't recognize it, going through the process of factor a quadratic trinomial, it's still always going to get you there. Well, number 2, same idea. If I recognize that perfect square and perfect square, well, if you've got perfect square and perfect square, just kind of check. If 4x squared would be 2x quantity squared. 9 would be 3 quantity squared. Well, if I check this, plus 2 times 2x and 3, well, 2x and 2 is 4, times 3 is 12. This needed to be negative, right? So that probably was a negative 3. And just like we talked before in the last section, if that number is positive, it's going to match this number right here. And you'll start to see that as you do more and more. So this right here, because it fits that format, I can see that it's automatically going to be 2x minus 3 quantity squared. Square root of the first term, square root of the last term, quantity squared. So that's the private factors, or that's the factorization for this perfect square trinomial. Again, if you don't recognize that right off the bat, then you can always go through and do it as a quadratic trinomial like we were doing before, and it'll still put you at the exact same place, 2x minus 3 quantity squared. It's a shortcut if you recognize it. Another type of special factorization for quadratics is the difference of 2 squares. If I have a perfect square minus a perfect square, it cannot be a sum of squares, it has to be a difference of 2 perfect squares. So first term squared minus second term squared is actually going to factor into the square root of the first term plus the square root of the second term, square root of the first term minus the square root of the second term. 16x squared minus 1. 16x squared is 4x quantity squared minus 1 is just 1 squared. That's probably the most commonly missed square root, is people forget that 1 is a perfect square. So since I have a difference of 2 squares, first term plus the second term, first term minus the second term. 14x, or 4x plus 1 and 4x minus 1. Now, again, if I don't recognize that difference of 2 squares, I can always make it a quadratic trinomial. I can write it as 16x squared plus 0x minus 1 and break it up into a pair of linear binomials. 16x squared is 4x and 4x. Negative 1 is plus 1 times negative 1. So let me check it. 4x minus 4x gives us 0x in the middle. So I can get the factorization the exact same way right there if I don't recognize it as a difference 2 squares. I can put the fact that there's no x's in the middle, put that 0x in there, and then just factor down. These are usually a lot easier to identify than the perfect square trinomials, so people usually have a better chance at seeing those and doing the question on the difference 2 squares. Well, number 2 here, x plus 2 quantity squared minus 25. This is actually, again, a difference of 2 squares. I think back when we did our common factor stuff, if we will identify what a term is. Terms are things that are added or subtracted. This is a term of the factor, or these are terms of the factor, or the first term. This is a term of the entire expression, because this whole expression minus this whole expression is combined together to give the entire expression. So these are the actual terms of the expression. Well, as we can see, this is squared, and we know 25 is a square. So when we factor, take the square root of the first term, so x plus 2 squared is x plus 2 and x plus 2. Break those. 25 is plus 5 and minus 5. So we can again see, following that same format, break down the first term, break down the last term. And it would all check out because you get 5 times it, minus 5 times it, gives us no term in the middle. And then we just clean it up. 2 plus 5 is 7. 2 minus 5 is negative 3. So that ends up being the final factorization of that. Now, that's it for quadratics. We can do common factor, identify a factor that goes into every single term. We can do just quadratic trinomials, x squared plus bx plus c. We factor it into a pair of linear binomials. Or we can see the two special products, difference of 2 squares and perfect square trinomial, that if we recognize them have a fast, a quick factorization because they always follow that same pattern. Now, as we get into class tomorrow, you're going to have a mixture of all of them, and you're going to see that you need to always check for a common factor first, because common factor shows up in everything. So if I'm always checking for common factor first, it can actually make what's left smaller and maybe easier to identify as one of these special factorizations. Quick example of how we would look for a common factor first. Call this example 5. So let's go with just 3x squared minus 75. Well, right now, it's a difference of 2 terms, but they're not both perfect squares. X squared is a square, but 3 is not a perfect square, 75 is not a perfect square. So if we look for a common factor first, 3 is a factor that's common to both terms and can go into both terms. So if I factor out that 3, I'm left with x squared minus 25, and now that becomes obvious that I have that difference of 2 squares. So x squared is x times x Negative 25 is plus 5 times minus 5. And this 3 doesn't disappear. We didn't divide it away, we factored it out. So it's still there. We've just moved it out of the x squared minus 25 so we can identify it. This is an example of a complete factorization. So always look for common factor first in every single type of problem. Then we can take whatever remains and see, is it a quadratic trinomial, is it a perfect square trinomial, is it a difference two squares, or is it something that just won't factor? And we're going to come across sometimes things that just won't factor. We'll have other ways to work with it. All right, I'll see you in class tomorrow, guys.